talk about a little about the exam. Oh, there's a homework with no name. If anybody looks like it might be yours, you should put your name on it. Maybe it's someone who's not here today. It's, page 206. Well, I can find out. So, I guess I'll start with just some basic information about the exam. The range is 99 to 45. The average was 84. Median was, this is math class, so we're just doing a little statistics here, just to give you a feel. And the mode, there was the mode 86, 3 people got an 86. Cool. And standard deviation of 15. You know, like 90% of the data is within 2 standard deviations, so I hope so. I learned some stuff correcting this. I'm really interested in the difference between someone not knowing something, being confused by it, or being fooled by it. So I examine these pretty carefully. If you make like a simple math error, I'm going to take a point off. If there's minor something, if you seem to kind of get it, I'm going to, but not, I'm going to give you some partial credit. If you just show just a minimal understanding of what's going on. These are all 5-point questions. You're going to get a point. If you completely have no idea, then you don't get any credit. I was happy to see that most people did really well on the derivatives, because I think that's the most important part of the section. Is derivatives. There was a few people got a little confused at various points with the between the chain rule and the product rule. I guess I'll let's look at number 17 for a second. The sign of x squared. You want to find the derivative. A few people somehow ended up with the sum, and I assume that's because they were, I know what they were thinking. Maybe it was the sine times x squared, maybe? I don't know. This is just chain rule, and it got me thinking along this really tortured path that I'm going to inflict on you for a minute. It may be useful, it probably won't, but there you go. So yesterday I saw once every couple of weeks they have a lecture, Wednesday afternoon. This week it was Professor Jennifer Chubb doing her research. She's interested in computability of graphs. She do kind of a graph that looked like this on the board. You know, graph is just kind of nodes and lines. And it was interesting. I didn't really get it. But computability has to do with, like, there's some questions you can ask about graphs and get an answer, like are these two nodes connected? And then you can have an algorithm that gives you that information. And then there are other questions that you can't have an algorithm. It's kind of an interesting question in math. You basically turn a question into what they call the halting problem. Then you know it can't be solved because the halting problem has been proved not to be solved. But we don't want to go into that. So anyway, I was looking at this, and at one point in the lecture, she kind of puts up this image she got from the internet. Kind of looks like this, and it had nodes and connections. And the brain is kind of a network. Yeah, okay. And that got me this morning thinking about your exams, thinking about a book I read very recently. It's called 1,000 Brains. Well, that's a goofy name. It's a guy who does research on how brains work, and it's very recent. I've never read anything like this. But, you know, you have your brain, and I can't draw very well. And it's evolved over billions of years. And the most recent part of your brain, you're Kai, right? No, you're Lara. Well, why don't you sit in your seat? That's what threw me off. Oh, someone's in your seat. Oh. Levy, I'm sorry. I'm distracted by my own ramblings. There we go. Did I give you? Oh, you did. Distracted by my distraction. So, the part of the brain that's most recent is the cortex. Mammals have cortexes. And it's kind of, it really sets us apart. One way to think of the cortex is it's like a large sheet, thin sheet. It's only like a few millimeters thick. But if you look at the cortex, they're these little, they're like columns. So, there's a column. And of course, you probably know that brain material is made of cells that are neurons. And some of the, within one of these things, this will make sense in a minute. Just go with me on this. We're in a math class. I'm not teaching biology or neurology. But there are these connections, and there's structure. There's kind of linear structure. And they're actually looking at this and trying to figure out what it does. So, interesting thing about the cortex, you know, it's kind of wrapped around your older brain. There's a lizard brain. Like, anyone here drive? Anyone here drive? Okay. So, you know, once you learn to drive after a while, you're just driving. You're not, you know, I mean, you might think, whoops, stop sign, but basically it just does it. And down here, your brain learns how to do all these things. If you're athletes, you know, hit the ball, you're not really thinking it through. So this is the part that's kind of thinking things through. And according to this guy's theory, see, this part of the brain doesn't actually have access to your nerves. This part does, you know, like move your legs or your arms. This part just kind of has to tell this part to do that. So it's just getting information and figuring things out. And his idea of what it's doing is it's creating a simulation. Okay, so I have my hand and it's moving around on the board. And as I move it this way, I don't expect something in the way, even though I'm not looking. I have a simulation in my head, right? I move it down, I run into this thing here. And that's all, it's all encoded in here. So when you come upon something new, these little columns are rearranging and learning things. Okay, what does that have to do with anything? So we have a problem here, and we have this idea called the chain rule, right? Derivative of composition of f of g is the derivative of f at g times g prime. Now, writing that down, you can memorize the letters, you can get an idea of what it means. But applying it is something that goes on, you know, it's a skill. It's like a pattern match. You have to kind of say, oh, that's a composition. That's like y equals sine of u equals x squared, and then apply these. Right? I guess we call this f of x, of u x. And we only get it the same way, you know, like when we're out, like playing, you know, learning to play tennis or driving. We have to practice it. And furthermore, you have to kind of practice it seriously. Like you want your brain to figure this out, which I know is really difficult because math is awful. It's terrible. We hate it. We hate it when we're learning it. You know, it's like, oh, it doesn't make any sense. It's hard. It's boring. I'd much rather be looking at TikTok. But you know, again, I'm thinking about this, and you know, thinking other, you know, when teachers sit around and say meaningless things, we have to get them excited about it. Excited about the chain rule. Oh, I don't know. I mean, you know, there's carrots and sticks. You know, I can try and give out chocolate chuckles, or you could do something punishing. But I can't really. This has to kind of come from outside. I have to think, okay, I gotta get over this hump where I look at these things, I see this, and I know, okay, derivative of sine is cosine of u times derivative of u with respect to x, that's 2x. But u is always x squared. Okay, so that's one thing I was thinking about this morning. The other thing I was thinking about was how, I mean, in a similar vein, how two of these problems I thought would be, well, one of them I thought would be a little tricky. We'll go over that one first. What is the limit? What is the limit as x approaches 0 of sine of 5x over x? Now, the majority of you did not get this at all. There were a few guesses. 0. Well, okay. It's not right. At least one or two guessed 1. That was a pretty good guess, because in class we went over the derivation of the derivative of the sine, and as part of that, an important point was that this limit of sine of x over x, as x approaches 0, is 1. And there was a homework problem. And I went over a similar problem with a different number. I showed you how to do it. But it wasn't exciting enough, I guess. And I had an idea, maybe I would have done better if I would have gone about it this way. I said, well, let's look at the sine of x, right? Let's do 0. Well, the derivative is the slope of the tangent at each of these points. Now, if you just kind of look here, if you look at a nice picture of it, you'll see the derivative is less than 1 at any point above here, but it's kind of heading down until it hits that point where it's 1. Now, you know, some people retain visual stuff better. I don't think they learn better, but they retain it better. So that, if you saw that, you might go, okay, well that helps me understand this. What do I do with this? Well, you know, do you remember pre-calc trigonometry, what happens when the coefficient here is greater than 1? What happens to that sine wave? Does it move out? Does it move in? Yeah, it squishes in. You could try a few points. You could try, like, let's say it wasn't 5x, let's say it was 4x. If you put in like pi over 2, well, you know, it moves it in. So 5x would be kind of the same thing, only from here to here, you get a bunch of these. And if you think about that, what's happening to that slope is getting bigger. So you might expect that this would be greater than 1, factor 5. And at that point, if you don't do anything else, you're just guessing, but okay. But the trick, as I pointed out, it was that you want to substitute here. Let's use a different variable. Let's say u equals 5x. So we have the sine of u over, well, x is going to be u over 5, or 5 up here. Now the limit, well, if x is going to 0, where is u going? It's going to 0. And now we have a problem we can solve. We know this is 1. So I don't think this is that important a problem. I don't think you're going to have that much, you know, unless you go on in math, you're not going to be dealing with limits that much. So I don't like this problem. I don't feel very good about it, but there it is. Number, you got it. Congratulations. Okay, so that was one that bothered me. There was another that bothered me even more. And I guess it goes back to this pattern matching thing. I like someone who, and you don't have to, Tracy, but like, since a lot of you didn't get this number 20. Someone who didn't get it, tell me if they recall what this is. This is important. We've used it a few times. We kind of left it behind because we don't need it, right? We have some rules to find what this is going to give us. Yes, Tony?
Isn't that the definition of a derivative? Or like, yeah.
Writing as big as I think I can fit. If we didn't have this, that whole section on limits would probably be removed from the curriculum. Okay, so I write something at number 20, I write some function is the limit h approaches 0 of, let's see, x plus h minus x, right? Over h, what went here? Cosine. Okay. So this is just, bear with me, I'm not trying to insult anyone. This is so obvious, but yet it fooled people. I think the reason it fooled people is because we're having an exam. You come into an exam and, you know, don't worry about the time, you have as much time as you want, okay, we're under time pressure. But they're like, oh, it's an exam. For decades, you go into class, exam, and it's like, math especially, oh crap. It does something, it's like the cortex shuts down and the lizard brain goes to work and it starts sweating and you get nervous. You have to try and avoid that. But I don't know how to teach that. I just know how to try and mitigate it. So all I'm asking here is, what's the derivative of the cosine? Which I hope everybody knows at this point. Okay, let me see if there's anything else I want to mention. There were a fair amount of like careless kind of things. Like if I pointed out, you know, like that's a 9, not a 0, you know, someone would get it. Now, I don't take much off for that. I try and figure that out and just, you know, slap on the wrist. A lot of people knew that the tangent has holes in it, right? It's not defined everywhere, but they didn't know where, and I guess that was under the circumstances where last year you were at school in COVID and maybe taking pre-calc. I can understand that. I tried not to take, I don't think I took too much off. You showed me you knew that there were holes in the tangent, you just didn't know where they were. A few times people like did the whole problem. It's obvious they got the answer, they know everything, and they just didn't state the answer. It's like, I don't know, is that nervousness during an exam? Again, I try not to take off more than a point for something like that. People did pretty well on derivatives.
guess there was a little confusion. Most people did okay on the tangent line. Now, what always impresses me is when someone says, kind of, you want me to do this? Heck with you, I'm going to do it this way. Someone, and I'm impressed, I like that. Someone took number 19, which is just screaming, do implicit differentiation, and solve for y, and found the derivative. Yeah. You know, math is not like always a one-way street. Okay. Any questions? Okay. If you did not do well on this, I implore you to come visit with me and go over this. Let's see if we can find out where things went wrong, how to repair them. Maybe it was just not enough attention, it was misunderstanding. Most people did pretty well, obviously. If you're a little underwater here, don't panic. There's plenty of time to get back above water, and I'll be at my office hours, obviously. Okay. Again, any other questions? Anybody else want to? Any problem or? This is probably a thing to leave up for the next section. By the way, I don't think we're going to get to it today because we have two topics. But the second topic, which we'll probably get to Tuesday, involves a lab experiment. I don't think you want to miss the lab experiment. There's lab equipment here. I promise it'll be exciting. Well, I shouldn't promise that. You might not exciting. Okay. Back over here. Good. So what we're going to look at today is something called a linear approximation. This is a applied technique. You will run into it in sciences, economics, and various places. It's kind of a tool for dealing with the real world, where you're dealing with measurements, and exact is not always what we're looking for. Theoretical math, we don't write down this, right? And we mean this, pi. But in the real world, there's always some accuracy that we can live with. So we start with this definition, but we're going to relax this limit thing here. Instead, we're going to say, well, if h is small, or if h is close to 0, but not at 0, then we don't need to use a limit here. We're only approximately equal, but it's approximately equal to f of x plus h minus f of x over h. It's an approximation, and clearly the smaller the h, the better. we might want to rearrange this by multiplying through by h. Since h is not 0, we can multiply by it. And then we're going to rearrange it one more time. We're going to put the f of x on this side, but I want to reverse it. So f of x plus h approximately equal to f of x plus h times the derivative at x. All right, so let's put something visual attached to this. We have some function, and we have some known point here, some x. So of course we have an f of x. And we're interested in f of x plus h. A little different. So what this is saying is, we find the tangent here. A straight line, if h is small, a straight line is pretty close to the function. Exaggerate here a little. So this is my h. So this point here, of course, is f of x plus h, which is what we're trying to estimate. And we estimate it as f of x plus h times, I'm going to just write m, the slope, is the derivative at x. Approximately. So that's the idea behind a linear approximation. We have some value, and we want to use what we know about derivatives to approximate value. Right. So that would be time for an example. Well, let's say our function is square root of x. Now, you might think, well, you get a calculator, it's got a square root of x plus, and I don't really need to do this. That's true. This is just an example to give you an idea. But imagine we have some function where that's not so easy. We do have its derivative, or God forbid, we have an approximation of its derivative. So here we know the derivative is 1 over 2 times the square of x. Well, the problem we want to look at is f of 104. Square root of 104. Now, using this strategy, we want to pick some nice numbers. I already picked a nice number here, because I can break this up into 100 plus 4. So this is my x and this is my h. All right, so what is this linear approximation formula tell me? This is approximately equal to f of x, which is 100, plus h, which is 4, times the derivative at 100, which is 1 over 2 times the square root of 100. Okay. I guess I can write here, this is the square root of 100. Okay, these are all easy numbers. This is 10.
times 4 over 2 times 10. Get rid of the 2 here, get rid of the 2 here. 10 to the 5th, that's 10.2. Well, how close is that? I'm going to use the old-fashioned method. I have a calculator handy. Okay, so when I recombine these, I see I'm pretty darn close, aren't I? 0.04 of 104. So that's the main idea. We can take a function and maybe these numbers work out so that we can do an approximation this way. Questions on this? Yes.
What did you do on that board? Or yeah.
What did I do?
Yeah.
I really feel like a dinosaur now. I did multiplication. Did I do something wrong? 2 times 2 is 4. 2 times 0 is 0. 2 times 2 is 2. And then I stick in a 0 because there's a 0 here. Just to move it over. I could put all zeros and then have another line. 1 times 102, 102. And then I add. I guess this is not as popular now with the advent of the electronic calculator, handheld calculator. However, when you're on that desert island and your batteries run dead, it's useful. Yes.
We were asking about why, we weren't talking about why it was wrong. We were asking why you did that. Like, why did you multiply?
Okay. Now I know I'm missing the point. Try again. You want to know why I'm doing this? Well, what was I trying to do? I was trying to find the square root of 104. I got this result using linear approximation, and I wanted to know how close am I? I mean, if you want to get out your calculator, you'll see it's 10.20 something, right? But I was just checking by, finding out x squared and doing the inverse and seeing how close I was back to 104. I think I missed the point the first time. I'm sorry. That's not what you meant. What was I doing? You knew what I was. Oh, all right, good. I don't know. About 10 years ago, I was teaching calculus to a high school student. This kid was the brightest kid in the class. He was just far and away, probably going to Princeton. He could do fractions. So I'm like, I don't know anything anymore. Okay, so we're not quite done. There's another question you can ask. Kind of hinted at that over here. What's the percent error in my approximation? So I have this component that I've added, right? I added it to the square root case to 10.
I take this and divide it by f of x. I'm getting the error between 100 and 104, approximately. And I can multiply it by 100, which will get me the percent error. I guess you can just treat that as like a formula. This again is only valid if h is small. So we have an example problem from the book. So here's the problem. A sphere, radius 3 inches, is incorrectly measured to be 3.1 inches. So part A is estimate the error in volume. And B is find this relative percent error. Okay. Well, clearly we need to know the formula for the volume of a sphere. Now, I'm not going to put this kind of problem on a quiz or a test, midterm, final, without giving you the formula. But at this point, I hope most of you are not shocked. Learn it's 4/3 pi r cubed. And the derivative, dv dr, is, everybody do this in their head now? This is,
4 times.
yeah, thank you, because you've illustrated something. I appreciate your bravery, because nobody else here was sticking up. This is what happens when you're on the spot. Your brain will switch things. You know the right answer, just there's a 3 there. You know, this is, sometimes I tell people my right hand sometimes has a mind of its own. It's kind of like that. The mind actually has many minds going on. Thank you, that's exactly right. 4 pi r squared. Okay, so our formula tells us what? Create another board here. So v of 3 plus 0.1 is approximately v of 3 plus 0.1, that's our h, times the derivative at 3. Actually, no. We'll finish this up and then we'll take a break. So that would be the error in the volume would be the difference between, what would it be? I guess that's the approximate, that's the difference in this is the approximate difference in volume. It's not the exact, That's not what we're asking for, we're just asking for an estimate. So the derivative at 3 is 4 pi times 9 times h, so it's going to divide by 10. And let's just do a quickie estimate. 36 times 3 is about 100. Is it? Yeah. 36 times pi is about 100 divided by 10 is about 10. So that's the error having measured 3.1 inches in our sphere. This, I guess I should say this cubic inches cubed. And relative percent error is going to be this value, this becomes 10 over the volume. Well, now we have to plug 3 in here, right? So actually, probably be better to leave it like this. 4 pi times 9 over 10 over 4 pi times 9 times 100. So we get a percent. So it looks like 0.1 times 100 or 10%. I think that's 10%. 1/10 times 100 is 10%. So actually, pretty big error for just such a small difference in volume. Yeah, I'm skeptical too. See if you can find an error in my calculation here. Times 21. I think that's right. Okay, why don't we take a break for a few minutes? We'll come back, we'll do a few problems. Go. In case you came in late, somebody turned in a homework with no name. I'd love to give someone credit. Can't be wrong, it could be bad. Anybody have some numbers? I mean, I know it's got to be 1/10 point something, right? Decimal point? Brave individuals. Yes.
10.33.
Okay. So obviously we would be looking for 1,000 plus 10. 10 would be my H. That would be cube root of 1,000 plus H. Oh, I skipped a step. I need to know f of x is, I'm going to write it this way to make it simple, cube root of x. And derivative has to be a third of x to the minus 2/3. Okay, so that's 10 times 1/3 1,000 minus 2/3. Oh, even I have to rewrite this a little here. So that's 10 over 3
times 1,000 to the 1/3 squared. Write it that way, because 1,000 to the 1/3 I know is 10. 10 over 3, 10 squared. Well, one of those is going to go away. 1 over 30. I think this is too big. There. Like that. That's good. Okay. All right, I think I'm going to stop for the differentials here. Differentials, linear approximation. This is not a big topic, but you know, you should be able to do one of these. As I said, they do come up in the real world, which we don't usually have here very much. Next subject, we're just going to get started on this. The next subject is a little bit a lot of people, it's kind of optional in this class. It doesn't fit in anywhere else. It's hyperbolic functions. These show up in math, in science, and told in architecture. And I've never done this before, so this experiment I may be looking really bad afterwards, but what I have is some bubble solution, and I have 2 hoops. And what I'm led to believe is that if I'm very careful, that I can form a surface I need more bubble solution. Up, anybody in the front? We may get it. Oh, no. Not quite right. It's holding together in the center. I need an assistant. Someone in the front row, quickly. It might explode if you don't come up here quickly. Oh! Try again. You're brave. Come here. You just have to pop the little bubble if I get it again. All right, now's your cue. Pop that little bubble in the middle. Do you see it? Stick your finger in there and it'll pop. See it? Oh, too late.
see what's going on. No. Good. All right, go ahead, try it. See what happens. Pop it. Yay!
Wow.
Okay, so that curve. Oh, I'm just going to hold it here until it pops. Oh, I'm so. Oh. Oh!
That was beautiful.
Okay. For my next trick, I will attempt to put a bubble inside a bubble. I don't know if this will work. It may be too dusty in here. One more try and then we move up for now. Well, we have a little one always. Okay, maybe after class. Okay, so what was that? Have a here, two hoops and a surface between them that attempts to minimize itself. And it turns out that this curve, taken, you know, if you do a slice, is a special type of curve. We're gonna see that today or tomorrow, I guess. Let me backtrack a little though. Get my once a year opportunity to use my little circle machine here. So we have something called either a trigonometric or sometimes it's called a circular function. And one way we define the circular functions is we take an angle theta for a unit circle, and we look at these coordinates, and the value of the x-coordinate we call the cosine, and the value of the y-coordinate, the ordinate, we call the sine of that angle. This gets us out of that problem with defining this in terms of triangles, where, you know, when we get to 90 degrees, we don't have a triangle anymore, and we can even go further. And we can have negative angles. So the function is defined on all reals. And let me just throw up here the equation of this circle is, of course, x squared plus y squared equals 1. We can do something similar if we have the equation of a hyperboloid, a unit hyperboloid. I don't have a handy device to draw this, but again, we can take points on this, and we can define define a new function. I'm going to use, actually use delta. This is, call it, you say cosh. Unless you're a fan of Babylon 5 and then you don't want to use that word. Cosine, hyperbolic sine. Now, good question is, well, what's this? I mean, here we know theta is an angle. As it turns out, if you draw a line here and mirror it here, fill in, the delta here is the area of this odd-shaped object. That would seem to make things inconvenient, except that it turns out there's a nice, clear, easy way to define these. We can, I'll go over here. I'll leave this up as long as possible. We can define a hyperbolic sine this way as e to the delta minus e to the minus delta over 2, and the hyperbolic cosine as e to the delta plus e to the minus delta over 2. And of course, it's not so obvious what it means, but we could also define hyperbolic tangent as the hyperbolic sine over hyperbolic cosine. So it's e to the delta minus delta over e to the delta plus e minus delta. And it might be useful to take a look at what these things actually look like. We graph them. So the hyperbolic sine is going to look a little like the tangent, but it's not periodic, and it doesn't have any holes in it. It just goes off forever. It's exponential. Hyperbolic cosine is quite similar, except that looks more like a parabola. And hyperbolic tangent well, it's going to draw this very well. It's going to become well, you can take a look at it. It's going to approach 1 or negative 1. It's going to be asymptotic. All right, so the little asterisk here. Hyperbolic cosine is exactly this shape here. So these are not totally just abstract mathematical oddities. There's some real worldness to them. And there are a lot of similarities between similarities. It's not the word I'm looking for. That's the word I'm looking for. I'll use similar. There's some very interesting similarities between the hyperbolic and the circular functions. We're going to list a few of them. Most of these, just knowing these definitions, you can derive them. One thing, you have some identities. So you're all familiar with sine squared plus cosine squared is 1. Over in the hyperbolics, these are circular hyperbolic. We have hyperbolic cosine squared minus the hyperbolic sine squared equals 1. We're going to see a lot of this where something looks similar, but there'll be a minus sign that'll change. I'll write it this way: 1 plus the tangent squared is the secant squared. For hyperbolics, it's 1 minus the hyperbolic tangent squared. I guess I should mention there's secant and hyperbolic secant and cosecant, which are defined just the way you think. 1 over the hyperbolic cosine is the hyperbolic secant, and so forth. So we have a hyperbolic secant squared. If you remember the sum formulas for sine and cosine, this is sine x cosine y plus cosine x. So I'm going to have to fit this. I have to squeeze a little. Cosine x sine y. With a hyperbolic, it's the same. For the cosine, remember we have cosine x cosine y minus sine x sine y. Here we have cosine x sine hyperbolic y plus, not minus, sine hyperbolic x sine hyperbolic y. I didn't do that right. This is a cosine. In a way, the hyperbolics seem a little more symmetric. Right? Okay. Another important thing to notice is the odd even relationships. You can just look at the formula and you can kind of pull these out, but sine is a odd function. Hyperbolic sine is an odd function. Cosine is an even function. Hyperbolic cosine is an even function. Now, we're in calculus, so we're of course interested in derivatives. I guess I should just do one. Should we do one derivative? The derivative of the hyperbolic sine of x. Just the derivative of e to the x minus e to the minus x. So you see how these go. Oh, this is real easy. Derivative of e to the x is e to the x minus derivative of e to the minus x. Well, that's e to the minus x times the derivative of minus x. That's the chain rule. You just get a minus sign, which is the hyperbolic cosine of x. All right, so let me begin, right? Derivative of the sine, cosine. Derivative of the cosine, everyone now knows, is negative sine. So here we have derivative of the hyperbolic sine. Is the cosine. But derivative of the hyperbolic cosine is just hyperbolic sine. That's what I mean. It's like they're even more symmetric. And just to complete this, the derivative of the tangent, hyperbolic tangent, is the hyperbolic secant squared. Just like the trigonometric functions. All right. All I'd really like you to take out of this section is this. That's the important thing. We have some functions. You take the derivative, you get of the sine, you get the cosine. You take the derivative again, you get back the sine. Kind of a two-cycle. Here we have kind of a four-cycle. Sine, cosine, negative sine, negative cosine, sine again. The rest of this is it's just so fun, I cannot keep it from you. I would be remiss. Some of you may recall from your pre-calculus, there's a important equation, e to the I theta equals, anyone recall how we phrase this up? Euler's equation? Cosine theta plus I sine theta. Well, this is all you need to derive the following interesting connections here. The sine, hyperbolic sine, you've already seen. I'm just going to use x. E to the x minus e to the minus x over 2. And hyperbolic cosine of x is e to the x plus e to the minus x over 2. You can define the sine, let's say theta here, in a similar manner. Sine of theta is e to the I theta minus e to the minus I theta over 2. And the cosine is e to the I theta minus plus e to the minus I theta over 2. And you can use Euler's equation, plug in here and verify that that's all correct. That's just a fascinating, look at that symmetry there. Except we have to involve imaginary numbers. It's very exciting. I think I have time for the last part here. This is definitely off the charts. You definitely don't need to know this semester. If you take Calc 2, you'll study something called Taylor series. Taylor series, well, we take something like e to the x, and we want to expand it as an infinite polynomial. We could call it a0 plus a1x plus a2x squared, so forth. And we want to look at what these coefficients are, these a's. So we do that. We start by plugging in x equals 0. So e to the 0 equals a0, and all this other stuff disappears. So we know that a0 equals 1. I'm going to write this as 1. I'm going to write this as 1 over 0 factorial for reasons you'll see in a second. Okay. The next thing I do is I find the derivative of both sides. Now this is e to the x. This goes away. a1 plus 2a2x plus 3a3x squared. And we pull the same trick. We set x equals 0. So here we have e to the 0 again equals 1. Now we have over here. It's 1 to the 0. 1 to the 1 over 1 factorial. Still 1. One more time, we find the derivative, e to the x. 2a plus 6a3x, so forth. Now we have, oh, I guess what I want here is x. X squared over 2 factorial plus x cubed over 3 factorial. Okay, that's the Taylor expansion of e to the x. We can perform the same operation with our other functions, and we would learn some interesting things, some interesting similarities. And this is just for fun, but sine of x, the Taylor expansion is 1 over 1 factorial x to the 1 minus 3 over 3 factorial x cubed plus 1 over 5 factorial. Minus. So the pattern is it's just the even terms, and every other term is a minus. Cosine of x is well, 1 over 0 factorial, x to the 0, that's just 1, minus 2 over 2 factorial x squared, plus 4 over 4 factorial x over 4. Okay, so again, now it's the even terms. Makes sense, it's an even function. And every other term is a minus. I'm going to do the abbreviated version of this. Make this the hyperbolic versions. Just get rid of the minuses. So this is, to me, just this beautiful symmetry in mathematics between, these hyperbolics and circular functions. You don't have to know all I'd like you to know is these derivatives. That's the only important part of this class, of this section. So, I have time for one more factoid.
You go look at the Golden Gate Bridge, where you create the rope over pedestals. You get that same hyperboloid hyperbolic cosine shape. And if you're an architect, and I don't know, you probably want to build, hey, we've got one right here. Take a look out that window. Apparently, the optimal shape to build a dome so that the stresses are exactly where they should be, give you the maximum, strength holding it up. It's again this hyperbolic cosine. So that's great. I hadn't even thought of it. I didn't have to draw it. You just take a look. So, okay, that's it for today. I will post a homework assignment that will be due next Thursday.